Thank you for the opportunity to present at the 2020 DMD conference. We are a group from Stanford, and we will be presenting a selectively compliant annuloplasty ring to enable annular dynamics and mitral valve repair evaluated by in-vitro stereovision. In a healthy heart, oxygenated blood flows into the left atrium through an orifice known as the mitral valve and into the left ventricle, where it will be pumped to the systemic circulation to provide oxygen to the rest of the body. When the integrity of the mitral valve is compromised, blood flows backwards into the atrium, leading to decreased pumping efficiency. This phenomenon is termed mitral regurgitation, or MR, and is the most prevalent cause of valvular heart disease. The mitral annulus is a ring of connective tissue that bounds the mitral valve orifice and anchors the mitral leaflets to the fibrous skeletal structure of the heart. The geometry and 3D dynamics of the annulus are thought to significantly contribute to valve integrity. Consequently, mechanical and geometric perturbations of the annulus, as are seen in MR, can lead to annular dilation, malcoaptation of the valve leaflets, and leakage. A major aim of surgical intervention is to restore annular geometry and ensure leaflet coaptation, and this is often accomplished through mitral valve repair with an implantation of an artificial annuloplasty ring. It is well known that the annulus is dynamic throughout the cardiac cycle, moving from a saddle-shaped conformation during systole to a flatter, more dilated shape during diastole. Current rings on the market, however, fail to consider these annular dynamics and could lead to undesirable tissue stretches and reduce mitral valve competence in the long term. Sam will now describe our approach to this clinical problem.
To address this need and enable mitral valve annular dynamics, we have created a selectively compliant annuloplasty ring. This ring consists of a nitinol core and 4 polymer segments that mimic the 4 primary morphologies found in a native mitral annulus. The manufacturing process begins with a thin piece of nitinol wire. We use a joule heating method to shapeset the nitinol in a 3D conformation that supports the formation of an annular saddle. Additionally, a PTFE filament is attached to limit the AP diameter. The 4 polymer segments are cast in a 2-part process, with the anterior and posterior sections cast first, followed by the left commissural and right commissural sections. We tested the ring in a porcine valve using the Stanford left heart simulator and compared the results to commercially available semi-rigid rings. The videos here show 3 example cases. At the top, no ring is embedded in the annulus, representing a dilated, unhealthy valve. Significant change in AP diameter is visible, as well as other undesirable characteristics. In the middle video, a commercially available semi-rigid ring is used. Even from visual inspection, it is clear that the commercial ring is greatly limiting annular motions. The ring simply moves up and down during the cardiac cycle. At the bottom, we see our custom ring. Unlike the previous cases, the custom ring is both stiff enough to correct the dilated valve and compliant enough to enable formation of an annular saddle, as well as other key properties of a healthy mitral valve. To quantify these properties and understand the motions in more detail, we use an in vitro tracking method. In order to minimize interference of measurement tools with biological structures when assessing annular dynamics, we opted for a computer vision approach to tracking fiducial markers. 4 types of rings were tested under analogous conditions in the left heart simulator. The first was a soft, low-stiffness silicone ring used to provide a baseline comparison. The second was a Physio2 ring, chosen as a representative case for commercially available semi-rigid rings. Cases 3 and 4 were our custom ring, named DynaRing, with and without the PTFE filament. Testing without the filament is done to explore the effect of limiting the AP diameter. Literature in the field has outlined metrics to characterize healthy mechanical performance of mitral annuli, and we characterize DynaRing using these same metrics. Specifically, we look at the anterior-posterior, or AP, distance, inter-commissural, or IC, distance, and mitral orifice area. In the figure at the top right, we compare the metrics for the 4 test cases, as well as a finite element model prediction of DynaRing's performance and literature control values of healthy annuli. The data shows that all 3 metrics for the control case were best matched by DynaRing with the PTFE filament. The poor performance of soft ring confirms the need for sufficient rigidity to stabilize the mitral valve annulus. On the other hand, the commercial semi-rigid ring prohibits natural annular compliance and results in rigid translation of the annulus. In contrast, DynaRing allows for in-plane variations and enables the formation of the characteristic dynamic saddle shape. Finer ring discretization with an increased number of segments may further improve results. Segment stiffness selection is an attractive feature of this product and enables the designer to match patient-specific requirements. In conclusion, DynaRing is a selectively compliant annuloplasty ring that has demonstrated similar dynamics as healthy annuli, outperforming semi-rigid rings in our studies. We look forward to your feedback to guide our continued design improvements.